Okay, here I have the goniometer with the specimen pin mounted on it. I'm just going to find the notch and mount it onto the spindle stage because we are going to be measuring the optical properties of this crystal. So I'm holding the goniometer and threading this onto the spindle stage. Notice I'm not holding the part that actually twists on the spindle because you can torque it while you're trying to thread that on. The notch will hold it so that you can thread it on. Here I'm trying to do a quick alignment of the goniometer. First, what I'm doing is just translating the rotation axis so that it's under the objective, under the middle of the objective, roughly. This is an iterative process depending on how far out of line it is, but you can make adjustments on the goniometer and the spindle stage axis. So this is roughly in position. It's rotating around an axis that's under the objective, but now I just translated the goniometer to the right, and then again to the right in this orientation, so that the goniometer is roughly at the axis of rotation. Except now this is a little bit too far to the left, so I'm going to translate it so that it's under the center of the objective again. And this will just give you a good starting position so that you can make your final adjustments when looking into the microscope. If the specimen pin or the crystal is too far past the middle of the objective, you can also translate the whole spindle stage or the goniometer translation screw back. So here I'm just going to do that on the translation screw so that the crystal is roughly in the middle of the objective line. So there we go. So now I'm looking into the microscope, and I also have a little inset video of outside the microscope, and you can see that we roughly got the crystal in the middle of the crosshairs just by eyeballing it, but we do need to translate the rotation axis down. Also keep in mind that the into the microscope view is going to be 180 degrees different from outside the microscope view. It doesn't really make much of a difference, but that's why it looks the way it does. So now the rotation axis is a little bit below the crosshair because I rotated it, and it rotated around an axis that's down there. So I need to bring it up a little bit, and that's pretty close, it looks like. It's rotating around the east-west crosshair line. But what I need to do now is translate the goniometer to that line in both axes. And actually that pretty much did it, just translating the one. Here I'm adding an oil cell so that I can see the crystal a little bit better. So now it's immersed in a refractive index liquid. And you can see the Becky line a little bit around the outline of the crystal. And now we have free reign over measuring extinction positions. The first thing that I'm going to do is acquire the reference azimuth. So I'm going to go to spindle 0 and rotate to extinction. And then I'm going to go to spindle 180 and rotate to extinction, and then enter in those microscope stage positions. So S is spindle, MS is microscope stage angles. And this is just to create an east-west reference line it should suggest a proper reference azimuth that you can enter there under MR. So I'm going to do that, and that'll be our first two extinction measurements. In this case, the way that this spindle stage is mounted, it's 180 degrees. It'll also mount to the stage at 0 degrees roughly. If you're using student spindle stages or some homemade thing, it might not be set up this way, and you have to enter in some random reference azimuth. So what I'm going to do is just repeat the process for spindle 10 degrees, 20, 30, and so on, and enter in those positions. And then once all the entries are made, then there will be an optical orientation solution plotted. So just repeat the process, and then once that's done, we will determine the optic sign of the crystal. And this is done by going to the coordinates listed on the EXCELIBR tab for the acute bisectrix line, which is AB. So I'm going to that position right now, which is spindle 93 degrees and microscope stage for an east-west lower polarizer of 198.5 degrees. And it should be at extinction when you insert the analyzer or the upper polarizer. Then what you do is rotate it 45 degrees so that the acute bisectrix line is parallel with the slow direction of this wave plate. And if it subtracts like it does, it's optically negative because the acute bisectrix line is alpha. So AB equals alpha, which means it's a biaxial negative geometry. And of course, if the opposite were true, it would be optically positive, and the acute bisectrix would be gamma. So you can enter that in with a minus sign on the EXCELIBR tab for biaxial inputs. The next thing that I'm going to do is I'm going to index some crystallographic planes because I can see some clearly defined on this crystal. And the way that this is done is you rotate the plane so that the pole to the plane is in the plane of the microscope stage. So in this example, this block, the screw is representing the vector that's going to index the plane that it's resting on. So now I'm tilting down so that the screw is into the plane of the stage, and then rotate so that it's east-west. I'm going to do the same thing with one of these planes here, or at least two of them actually. So I'm rotating that plane that's on the bottom. It's now kind of greenish purple. So that line is oriented north-south, and the pole to that plane is oriented east-west. So I'm going to index that as some HKL, and that's at 24 and 262 entry. And here's the second plane that I listed there. And these planes intersect along a vector that's parallel to the long axis of this crystal. So, for example, if that was the C-axis, these would be HK zeros because they don't intersect the C-axis. And since I just indexed those two planes, the program will take the cross product of those two planes and calculate the position of a possible crystallographic vector. So if it was an amphibole and you were indexing the 110s, those two planes would intersect along the line of the C-axis. In this case, this is scolecite, and depending on what lattice setting you use, those planes will intersect along the A-axis and possibly the C-axis if you're using an old lattice.